In this lecture, we're going to talk about priority queues, their implementation using heaps. And since we've got heaps around, we're going to go ahead and talk about heap sort as well. Heap sort is an optimal algorithm asymptotically for time. To present this, I'm going to be looking at some notes from the textbook as well as some other tests. The notes are collected here. A lot of the data structures that we've seen are collections in the sense that you put things in, you get things out, and the way they vary is in terms of how you get things out. So for example, we had a stack where the thing we got out was the most recently put in, or the last thing put in. And we also had a queue where we take the oldest thing in the queue, or the first thing put in. There's also a notion of a randomized queue, which we haven't talked about, but you can imagine an implementation where we just get a random element out of the things that are remaining of what we've put in. What we're going to talk about today is a generalization of all these things, which is a priority queue. A priority queue is where we have some notion of order on the elements, and we're always going to take the smallest or the largest element of those remaining. Now you can think of this as a stack where we're simply putting them in according to their timestamp, where time is increasing. And then in a stack, we're taking the greatest one. In a queue, we're taking the least one. And then with a randomized queue, the order would simply be some random number that you're assigned when you go in. Thus, priority queues sort of generalize all these things. You can see an example here where I insert P, Q, and E, then take out the maximum element. And here afterwards we insert X, A, and M. If we remove the max, we'll get X. Note that Q's already been taken out, so if we keep inserting, we won't get out Q again because it's already come out. When we remove the next max, we'll get P. It's not difficult to think of examples of priority queues. It used to be that airlines used to use a queue for boosting people up from one cabin to the other. And now they use a priority queue. So you need to have a certain status with the airline and whatever. I don't know what their algorithm is, but they've got some way of establishing the priority of customers, and whoever has the highest priority is going to be at the front of the queue. You can also think of the bouncer at some nightclub who's picking people out of the line to go in based on some idea in his head of which ones he should let in. There's some priority algorithm there, and it's not always who came first. Priority queues are often used as a component of a larger algorithm. For example, in data compression, we use priority queues to keep track of the most frequently used letters. You'll see this in data structures too. You might also see in data structures too an example of graph searching using Dijkstra's algorithm. If you take any AI classes, you're bound to learn the A-star search algorithm, which also uses a priority queue to figure out which branch of a search tree to look at first. Spam filters, firewalls, the list goes on and on. So how do we implement these things? The interface that the book emphasizes is the maximum-oriented priority queue. It looks something like this. You can create one of them. You can insert a key. You can delete a key. You can ask whether or not the queue is empty. And note here, when you delete something, you're always taking out the highest priority item, in this case for a max priority queue. So that'll be the largest key. And the delete max returns that key. You can also just check who's at the front of the queue using the max function without removing them. Suppose we want to do some analysis on bank transactions, and we've got trillions and trillions of transactions to look through. We want to find the largest items in that list. Maybe we want the largest million of them. And note that when we have a trillion data items, we may not even be able to fit all of this in our memory. And therefore, it may not be possible to sort those things in memory. And that becomes a problem then. How are you going to find those million highest priority transactions? It's really easy with a priority queue. What you can do is just simply fire one off, read in all the transactions, and as you're reading them in, add them into a queue. Whenever you find that you've run out of room in memory, you just delete the minimum ones. So you take out the ones that don't matter. So you can think about how much time and space these solutions take. If we were to try and sort in memory, well, we'd need memory proportional to all the items, so that's all the trillions of items. And we'd take time proportional to n log n. This is the fastest that we can do a comparison-based sort, and we'll see one sorting algorithm that actually works in this time today, that's heap sort. If we use a priority queue, we can avoid storing all these trillions and trillions of elements and just store the millions of elements that we need. We'll still have to worry about the time complexity though. If we are required to look through each of those millions of elements for all of the trillions of elements that we look at, then we're going to have a multiplier. This will be the trillions times the millions. And that may not be acceptable. We'll find that we can speed things up quite a lot using a binary heap. In that case, each of the trillions of elements can be processed in log time, where we're just looking at the log of the millions that we have to store. In order to allow us to compare priority queue implementations experimentally, I've written a little test file here, and it's going to work with this interface. So we're going to work with minimum priority queues where the elements are doubles. So this just simplifies the coding a little bit. We don't have to worry about comparable and comparator and all that business. We're just going to use less than and greater than. In order to talk about elements that are missing, I'm just going to not allow 0 as an element. So we're just going to have non-zero doubles. The test code I have allows you to run a specific test. So we'll be working through this example from the text. And you can run other tests as well. And then we've got, of course, a doubling test where we'll look at the performance over time. In order to simplify the implementation, we're just going to use a fixed capacity priority queue. The first implementation we'll look at just sorts the elements in increasing order. And I've written the whole file down here. It's got quite a lot of stuff in it. We have in, we have the array A, we have some methods just to get us started here. The constructor just creates an array of the appropriate capacity. And the insert method does things, the min, the delete, and we have an exchange. The exchange is just going to swap elements at A of I and A of J. There's also some stuff in here to actually visualize and to deal with errors. And for the most part, that's a distraction, so I will skip to looking really just at the insert and delete method. The significant elements of the array are going to go from 1 up to n, inclusive. That's not like we've normally encoded it where we go up to n minus 1. In this case, we're really going to go from 1 to n. I can implement insert using the same approach we used in insertion sort. So I'm just going to increment n and write x into the nth position. Then I'll go from j, starting at n, down to 2, as long as a of j is less than a of j minus 1. So if the nth element is less than the nth minus 1 element, well, I know it's an inversion, so I need to flip them. And so I'll just do this until either I get to the end of the array or they're in the right order. Note that I have to do a little work when I do delete as well. So here, if I'm deleting the minimum element, it's actually going to cost me something. And why is that? Well, I need to then move all of the other elements over. So they have to all be shifted down by 1. And you can see this in the coding. So the result of a delete is just going to be the first element. But then I need to go for 2 up to n and move them all down 1. And that's annoying. I'll just zero out the nth element to say that it's not significant anymore, and then decrement n. This seems like we're doing too much work. And in fact, the numbers bear this out. So if you run an experiment on this, you'll see that inserting 130,000 elements is taking about 4 seconds. Deleting 130,000 elements is taking about 17 seconds. So this is just random data. We're in 2 phases. We're going to do a bunch of inserts and then a bunch of deletes, and then we're just watching to see what happens. So insertion here is linear time for each insert. Delete is linear time for each delete. So what we're seeing here is quadratic performance. because we're doing in inserts and in deletes, and therefore in times in squared. Note that delete is a little bit more expensive than insert, about 4 times as much. Why is that? Well, on insert, we can get lucky. We can, get something that is randomly sort of in the middle or toward the end. But with delete, we're never getting lucky. We're always having to move everything over. I mean, this is just dreadful. And so that asymmetry sort of informs how we might be able to improve this. Why are we doing it in increasing sort? Why don't we just make it a decreasing sort? And if we do that, well, we can not complicate insert at all. We just change the sign of the operator, that's all. And delete gets dramatically simpler. What happens here? Well, we can just take the last element. Yay, done. And then we just decrement in. And you can see the performance is, of course, much, much better. Delete has now become constant. Insert is still, the same. We haven't changed anything. So for 130,000, it's still taking 4 seconds. But just by switching the way we're sorting, we've gotten a dramatic increase. But why are we keeping this thing sorted? Why don't we just throw things at the end? And then we don't have to sort them as we go in. Then we're going to have to pay a little bit to get things out because we no longer know where the minimum element is. It could be at the end, it could be in the middle, it could be sort of anywhere. So what are we going to do? We need to code up a loop to find the minimum. The nice thing, though, is that once we find the minimum, it's easy to remove. We can just swap it with the last element, then zero out the last element and decrement. There are other faster ways to code that, but this is fine for our purposes. And what kind of performance do I get? Well, it's kind of what you expect. Insert is now rockin' fast. In fact, it's constant time. Whereas delete minimum is linear time. So we've inverted the costs we had before. Before we had insert being linear and delete min being constant. Now I've got the reverse situation. Insert is constant, delete min is linear. Wow, wouldn't it be nice if I could just have both of these things? It turns out that that is impossible. So getting constant time for both these operations just isn't going to work. But I can get log time relatively easily. We're going to do this using something called a heap. The heap here has an insert which looks a lot like the insert we had before, and the delete which looks a lot like the delete we had for our original delete min. And all we're going to do is add a bit of code here to maintain some invariance of the data structure. Not quite sorted, but kind of sorted. It's going to be what we call a heap. And when we do this, we're going to get pretty good performance. We get, for 130,000 elements, we're down in milliseconds, 14 milliseconds for insert, 30 milliseconds for delete. And just compare that with our prior implementations, where for 130,000 elements, one of our operations was, taking seconds. So either delete min at 8 seconds or our insert at about 4.5 seconds. These are just not acceptable numbers for 130,000 elements. We should not be taking 4 seconds. And with a heap, we get these numbers down to things that are much more sensible. So we can handle much larger data sets. We can look at 33 million elements and still do all that with the insert in under 2 seconds. Note that delete min is getting kind of expensive here. So our practical size, if you like, things that we can do in under a second is still about 2 million. But that's a lot better than what we were getting before. You can see that the algorithms for swim and sync are a little bit more complicated than the algorithm for min position. Min position is just one linear swipe through an array. The swim and sync operations are trickier, so I'll talk about them in a separate video.